Hello, and welcome to Quiet Learning for Sleep. This is your peaceful space to unwind, to let go of the day, and to drift into deep, restful sleep while learning softly about our universe. Here, we take gentle journeys through calm ideas, stories from science and nature, space and time, history and life, all whispered at a soft pace, without rush, without noise, and without pressure. You do not need to focus or remember anything. This is learning the quiet way, where your mind floats and drifts and rests, while curiosity stays softly awake in the background. If you'd like, before you get comfortable, you can subscribe and gently like this video. Doing it now means you won't forget later, and it helps others like you find this calm, sleepy corner of the world. Now, allow your breath to slow just a little. Let your shoulders relax. Let your thoughts soften, like clouds drifting across a calm evening sky. There is nowhere you need to go, nothing you need to do, and nothing expected from you here. This time belongs to rest, comfort, and gentle curiosity. And if you drift to sleep along the way, that is not only allowed, it is welcome. So settle in, let yourself melt into stillness, and allow your mind to float quietly as we begin. Long before the first stars came to life, the universe was nothing but darkness and potential. Space had only just unfolded from the first great burst of creation, an event so hot and dense that matter and light were inseparable. As the newborn cosmos expanded, it began to cool. Particles that once moved too wildly to bond started to cling together. Protons, electrons, and neutrons, forming the simplest atoms, mostly hydrogen, with traces of helium and a whisper of lithium. For nearly 400 million years, there were no stars, no planets, and no galaxies. Only vast, invisible clouds of gas floated through a dim haze of afterglow, the cosmic microwave background, a fading echo of the universe's own birth cry. Gravity, the quiet architect, began its slow work. It gathered atoms into denser regions, subtle ripples born from quantum fluctuations in the very first moments of time. These invisible patterns became seeds of structure, destined to grow into galaxies. Yet in this age before light, the universe slept, waiting for its first sunrise. Inside those ripples, hydrogen clouds thickened. Over tens of millions of years, their centers grew warmer under the relentless pull of gravity. At last, pressure ignited nuclear fusion, and the first stars burst to life. The darkness broke. These were titans, massive, short-lived suns, burning hotter than any that would follow. Their light spread across the cosmos, reionizing the gas that had cloaked everything in shadow. Where once there was only cold hydrogen, there was now radiation, heat, and ultraviolet light. The epoch of illumination had begun. But these first stars were also fragile. In mere millions of years, an instant in cosmic time, they exhausted their fuel and exploded as supernovae. Their violent deaths scattered new elements, carbon, oxygen, iron, into the surrounding void. For the first time, the universe contained the raw ingredients for planets, oceans, and life. Creation had begun to recycle itself, each generation of stars leaving behind the materials needed for the next. As eons passed, groups of stars collected under gravity's steady hand. Small proto-galaxies formed, irregular swarms of light dancing within halos of dark matter. These young galaxies drifted through space, like glowing embers carried on an invisible wind. Some merged, combining their stars and gas into larger, brighter systems. In one corner of the universe, roughly 13 billion years ago. A growing concentration of such galaxies began to fall together. Their collisions were chaotic, yet strangely creative. Every impact triggered new waves of star formation. Out of this cosmic turbulence, a larger, more organized system began to emerge. It was the early ancestor of our Milky Way. At its heart, massive stars lived and died in quick succession, feeding a central region of high density. In time, a black hole formed, born from the collapse of one of these early giants. Its immense gravity became a silent engine, shaping the matter around it into a spinning disk. The seeds of the Milky Way's core had taken hold. Beyond the newborn core, gravity continued to weave its tapestry. Streams of gas spiraled inward, forming the first faint arms around the center. The young galaxy shone blue-white, full of restless newborn stars. But between those bright clusters stretched immense darkness, great rivers of dust that absorbed starlight and hid nurseries of future suns. The Milky Way was not yet the majestic spiral we see today. It was lopsided, turbulent, and alive with collisions. Small dwarf galaxies slammed into it, each impact stirring the disk, reshaping its rhythm. Their remnants still linger in the outer halo, ancient clusters of stars moving in ghostly orbits, relics of those early mergers. With every collision, the Milky Way grew larger, brighter, and more complex. It was a living structure, feeding on the universe around it, learning, through gravity's patient lessons, how to become a galaxy of order and grace. While the galaxy matured, the physics of its heart settled into a delicate balance. The supermassive black hole, now millions of times heavier than our sun, spun quietly at the center, surrounded by a glowing halo of gas. Each time a star strayed too close, it was torn apart, releasing brilliant flares of radiation that could be seen across millions of light years. Yet for the most part, the core rested, an immense, dark heartbeat, marking the passage of cosmic ages. Around it, stars orbited in grand harmony, their collective gravity maintaining the spiral's elegant shape. The galaxy's arms became better defined, stretching tens of thousands of light years through the thin galactic disk. Hydrogen clouds flowed along those arms like rivers, condensing here and there into new generations of stars. Slowly, the chaos of youth gave way to a calm, ordered rhythm. The Milky Way had reached a kind of maturity, though it was still young compared to the universe itself. It would take billions more years for our sun, and our story, to appear within one of those arms. Now, if you could drift back through time and watch this vast formation unfold, you'd see beauty in slow motion, glowing filaments of gas weaving together, dark matter scaffolding providing the invisible framework, collisions birthing light and chaos, then silence again. You'd watch the Milky Way rise from darkness like a spiral of smoke illuminated by starlight. Every atom that now makes up our world, every molecule in our oceans, every breath you take, was forged in those ancient furnaces. The heavy elements in your blood once blazed at the hearts of stars that died long before the sun existed. The history of our galaxy is the history of matter, learning to shine, to collapse, and to rebuild itself. And as you drift deeper into rest, you can imagine yourself as part of that endless cycle, born of stars, returning to silence, a small but eternal note in the vast symphony of the cosmos. The Milky Way is no longer a mystery. It is our ancestor, our home, and our cradle in the infinite dark. When the first stars were born, they were unlike any that exist today. The universe was still young, less than 1 billion years old, and the gas from which those stars formed was pure, made only of hydrogen and helium. There were no metals, no dust, no heavy elements to help cool the clouds and slow the collapse. As a result, the first stars were enormous, hundreds of times more massive than the sun, blazing with intense blue-white light. They lived fast and died young, burning through their fuel in just a few million years. Their light transformed the cosmos, ending the long darkness that had followed the Big Bang. This moment, when the universe first filled with starlight, is called the epoch of reionization, the great awakening of light itself. The radiation from these first stars reshaped everything. It heated the intergalactic gas, tore electrons from atoms, and cleared away the mist that had hidden the early universe. For the first time, light could travel freely through space. Distant regions that had been isolated could now influence each other, their starlight overlapping like ripples meeting on a pond. The cosmic web, the vast structure of filaments and voids that still shapes the universe today, began to glow faintly, illuminated from within. The earliest galaxies appeared as small, irregular gatherings of stars orbiting each other in chaotic motion. They were primitive, unrefined, and yet breathtaking in their raw energy. If you could stand within one, the night sky would not be black. It would shimmer with countless brilliant suns, so close together that shadows would hardly exist. Inside these first galaxies, gravity worked tirelessly, drawing gas into dense knots where new stars were born. Each generation enriched the next. When massive stars ended their lives as supernovae, they seeded their surroundings with heavier elements: carbon, oxygen, silicon, and iron. These were the materials that would one day form planets, mountains, and living cells. The first dust grains condensed in the cooling remains of dying stars, drifting through space, and providing the scaffolding for new stars to form more efficiently. The universe had begun its long process of chemical evolution. Over time, this cycle of birth and death gave rise to more complex, stable galaxies. Among them was a gathering of stellar clusters and gas that would one day become the Milky Way's ancestral form. As these early galaxies grew, they began to merge. Each collision was an act of both destruction and creation. Stars rarely collided directly, but their orbits were violently disturbed. Gas clouds compressed under tidal forces, triggering furious waves of star formation. The result was chaos sculpting beauty. Out of the wreckage of smaller galaxies came larger, more structured ones. Our proto-Milky Way grew through such mergers, absorbing smaller neighbors, gathering mass and momentum. At its center, gravity deepened into a powerful well, anchoring the galaxy as its spiral nature began to emerge. Dark matter, the invisible skeleton of the cosmos, provided the unseen foundation, ensuring that even as chaos raged, the growing galaxy held together. By this time, the universe was about 2 billion years old. The first stars, the ancient population 3 suns, had all died. Their light long faded, but their legacy remained. The new generations of stars were smaller, more stable, capable of living for billions of years. Many of these still shine today, hidden in the Milky Way's oldest clusters. In their light, we see the fingerprints of that earlier time, the chemical signatures of the first supernova, written across the spectrum of starlight. Astronomers can read those patterns like fossils in the sky, tracing the ancestry of our galaxy. Every atom heavier than helium, from the calcium in your bones to the iron in your blood, was forged in those ancient furnaces. The universe had not only created stars, it had begun to create the ingredients of life itself. The darkness between galaxies grew less empty as more stars formed. Light now filled the cosmos in every direction. The great age of illumination had arrived. From this point onward, the universe would never again be truly dark. Galaxies bloomed like constellations of fireflies scattered through the night, drifting apart as space continued to expand. Somewhere among them, the young Milky Way continued to take shape, a glowing spiral of creation, still humble among the giants of the universe, but destined to become one of its grandest structures. And so, the story of light became the story of form, as the cosmos learned to shape itself not only with energy, but with memory, rhythm, and grace. Deep in the heart of the forming Milky Way, gravity began to weave one of its most extraordinary creations, a galactic core. Here, the density of matter reached unimaginable levels. Stars orbited so closely that their light blended into a luminous haze, and at the very center, a singular mass was forming. It began with the collapse of one of the earliest giant stars, a relic of the chaotic mergers that had shaped the young galaxy. When its nuclear fuel ran out, it imploded under its own weight, creating a black hole, an object so dense that not even light could escape its pull. Around this dark seed, gas and dust swirled in an accretion disk, heated to millions of degrees by friction and compression. It glowed in X-rays, invisible to human eyes but bright enough to outshine entire clusters of stars. Thus, the Milky Way's central engine was born, Sagittarius a star, the silent conductor of our galactic symphony. As the black hole fed, it shaped the galaxy around it. Each burst of infalling gas released enormous energy, creating jets that pierced the surrounding space. These jets, traveling at nearly the speed of light, injected heat and momentum into the interstellar medium. Paradoxically, this violence helped bring order. The jets prevented too much gas from collapsing at once, regulating star formation and stabilizing the galactic center. It was a cosmic feedback loop, energy flowing outward, even as gravity pulled inward. The balance between these forces allowed the Milky Way's heart to settle into equilibrium. Physicists call this state dynamic stability, chaotic on a local scale, but harmonious when seen across millions of years. Within this balance, the first long-lived stars began to trace orbits that would persist for billions of revolutions around the core. If you could hover safely near that ancient center, you would witness an astonishing dance of physics. Stars whirled in elliptical paths at hundreds of kilometers per second, their motion governed not only by visible mass, but by an unseen halo of dark matter. Every orbit carried a whisper of general relativity, light bending around gravity, time itself running slower near the core. Occasionally, a star would wander too close, torn apart by tidal forces so extreme, they stretched it into ribbons of plasma. The debris spiraled inward, vanishing beyond the event horizon, releasing one final flare of energy before disappearing forever. This process, known as tidal disruption, still occurs today, rare but measurable, one of the few direct signs of a black hole feeding in our galaxy. Over billions of years, this central region evolved into a kind of cosmic city. Stars of all ages moved through it, some ancient, some newly born in dense molecular clouds. Astronomers call this environment the nuclear bulge, a crowded sphere of 100 billion suns, packed into a region only a few thousand light-years wide. Within it, the average distance between stars is far smaller than in our solar neighborhood. Radiation, magnetic fields, and stellar winds form a chaotic weather system on a galactic scale. Yet, somehow, stability endures. The black hole at the center acts like a gravitational anchor, keeping the entire structure from flying apart. Every orbit, every cluster, every cloud participates in a balance between chaos and order, a cosmic version of entropy held in suspension. The existence of such a regulated system raises profound questions in physics. How can gravity, a force that only attracts, create such endured complexity? The answer lies in the way energy redistributes itself. Every collapse releases heat. Every collision spreads motion. Entropy always increases, but not evenly. Galaxies are the universe's way of managing disorder, transforming energy gradients into long-lived structures. The Milky Way's core demonstrates this perfectly. Local turbulence feeding global symmetry. In its magnetic fields, in the oscillations of its stars, in the precession of their orbits, the laws of thermodynamics, relativity, and quantum mechanics all meet. Each rule plays its part, like instruments in an orchestra, creating harmony from the raw materials of chaos. And so the galactic core became both the heart and memory of the Milky Way. Every orbit, every pulse of radiation, every flare of X-ray light carries a record of its past. Around it, the spiral arms stretched outward, tracing elegant patterns through the dark. Beyond those arms, the halo extended, full of ancient stars, the fossils of earlier galaxies long absorbed. The Milky Way had found its rhythm. The violence of its youth had given way to enduring motion. The black hole no longer raged. It simply waited, patient and immense, guiding the dance of 200 billion suns. From this calm center, the story of our galaxy would continue outward, into the spiral arms, the interstellar medium, and eventually the birth of a small yellow star that would change everything. But that part of the story is still to come. Stars are the forges of the universe. Every element heavier than hydrogen owes its existence to their inner fire. Deep within a star's core, gravity squeezes matter so tightly that atomic nuclei collide and merge. This process, called nuclear fusion, transforms hydrogen into helium and releases energy in the form of light and heat. The balance between gravity's inward pull and the outward pressure of radiation keeps a star stable for millions or even billions of years. But this balance is temporary. When a massive star runs out of fuel, gravity wins, and the story turns violent. The core collapses within seconds, crushing atoms, fusing heavier elements like carbon, oxygen, and iron in one final blaze of thermonuclear fury. The result is a supernova, an explosion so powerful it outshines entire galaxies for a brief moment in time. During those few seconds, physics reaches extremes beyond imagination. The temperature inside the collapsing core climbs to billions of degrees, and the density rivals that of an atomic nucleus. Neutrinos, ghost-like particles that rarely interact with matter, stream outward in a flood, carrying away energy and triggering shockwaves that blast the star's outer layers into space. Those layers are filled with new elements forged in the explosion: gold, silver, uranium, and dozens more. The expanding debris becomes a supernova remnant, a glowing cloud of gas and dust traveling through the interstellar medium. Over thousands of years, it cools and spreads, mixing with the galactic winds that drift between the spiral arms. In this way, the ashes of dead stars become the raw material for new ones. The Milky Way learned early that destruction and creation are not opposites. They are partners in a cycle that never ends. If you could see this process across millions of years, it would resemble breathing. Clouds of gas collapse, ignite, and then scatter, each cycle enriching the galaxy with new elements. Astronomers call this process chemical evolution. Over time, regions of the Milky Way became progressively richer in metals, the astrophysical term for all elements heavier than helium. Our galaxy still bears the gradient of this enrichment. Older stars in the halo contain almost no metals, while younger stars in the spiral arms are loaded with them. Each generation of stars has literally rewritten the periodic table of the cosmos. Carbon for life, oxygen for air, silicon for rock, iron for blood. None of these existed in the early universe. They were forged in stellar hearts and scattered by explosions that lit up the darkness like cosmic fireworks. Among the countless types of stars born during this era, some died in even stranger ways. When stars between 8 and 20 times the mass of the Sun exploded, they often left behind neutron stars, spheres only a few kilometers wide, yet heavier than the entire Sun. Inside them, matter is so dense that protons and electrons merge into neutrons. The surface gravity is unimaginable. A teaspoon of neutron star material would weigh billions of tons on Earth. Some of these remnants spin rapidly, emitting beams of radio waves that sweep through space like cosmic lighthouses. Others drift quietly, cooling for eternity. And in rare cases, when the progenitor star was truly colossal, its collapse went even further, creating another black hole. These remnants are scattered throughout the galaxy like punctuation marks in the story of creation, reminders that even endings have purpose. Supernovae also play a hidden role in shaping galaxies through feedback. The shock waves they send out compress nearby gas clouds, triggering new rounds of star formation. At the same time, the energy they release can push matter outward, clearing space for future generations of stars. It's a galactic rhythm of pressure and release. In this way, the Milky Way maintains a delicate equilibrium between chaos and structure. Astronomers studying supernova remnants today, like the Crab Nebula or Cassiopeia A, see not just destruction, but architecture. These remnants sculpt the interstellar medium, create turbulence, and even seed magnetic fields that guide charged particles across vast distances. Without supernovae, the galaxy would stagnate. With them, it breathes and evolves like a living organism. Eventually, within the enriched spiral arms, new generations of stars began to form from the debris of the old. These clouds were cooler, heavier, and dustier than before, perfect conditions for building complex systems. Among the atoms in those clouds were the elements of life waiting to assemble: carbon chains, simple amino acids, frozen water, and silicate grains that would one day become rock and soil. As gravity pulled these materials together, the seeds of future planets were born. The galaxy had entered a new phase, one not just of light, but of chemistry, complexity, and potential. The fires of creation had built the tools of life, and though no mind yet existed to observe them, the universe had already set the stage for all the wonder that would follow. The Milky Way was no longer just a structure of stars. It was becoming a cradle for possibility. By now, the Milky Way had gathered enough mass to define itself. Clouds of gas and stars revolved in great arcs around the galactic core, drawn by gravity, yet sustained by their own angular momentum. Rotation transformed chaos into order. The faster-moving inner regions dragged ahead of the outer ones, stretching pockets of gas into sweeping curves. Over millions of years, those curves stabilized into spiral arms, great rivers of starlight threading through the disk. Astronomers call these structures density waves, slowly moving patterns of compression that trigger star formation as they pass. Each arm is not a fixed line of stars, but a traveling rhythm, a standing wave of gravity and gas. It is as if the galaxy breathes, its luminous arms expanding and contracting in cycles measured in hundreds of millions of years. At the heart of this motion lies a puzzle that challenged modern physics. Stars far from the center move almost as fast as those near it. According to Newtonian gravity, orbital speed should decline with distance, just as planets in the solar system slow the farther they are from the sun. But observations of hydrogen clouds in the Milky Way show otherwise. The outer disk refuses to slow down. This discrepancy led astronomers to an astonishing conclusion. Most of the galaxy's mass is invisible. Dark matter, an unseen halo enveloping the entire Milky Way, provides the extra gravity needed to hold everything together. Though we cannot see or touch it, dark matter outweighs all the stars combined. Without it, the spiral arms would fly apart like sparks from a wheel. With it, they endure, turning in perfect synchrony around the galactic core, the bar at the center of the Milky Way, the elongated structure of stars crossing its core, emerged from these same rotational forces. As stars orbit, their collective gravity can amplify certain resonances, much like vibrations on a string. Over time, those resonances organize matter into a bar that channels gas toward the center. This inflow fuels both new star formation and the supermassive black hole's faint appetite. The bar acts as a bridge between the inner and outer galaxy, redistributing angular momentum and maintaining the spiral pattern. From afar, the Milky Way now resembled a cosmic whirlpool, arms of light swirling from a radiant heart, a masterpiece of self-organization, sculpted by gravity alone. Within the arms, the cycle of creation accelerated. Shock waves from supernovae compressed nearby gas. Magnetic fields guided the flow of charged particles, and molecular clouds collapsed into clusters of newborn stars. These clusters lit the arms in patches of blue and white, the signature of youth. Between them lay regions of darkness, nebulae of dust, where future generations would gestate. The interplay of light and shadow gave the galaxy texture and depth. Viewed edge-on, the Milky Way appeared as a thin, glowing disk, bisected by a dark lane of obscuring dust. From within, it would look like a vast river of silver stretching across the night sky, a sight our distant descendants on a future Earth would one day name after the taste of milk and the memory of wonder. As the spiral arms matured, the Milky Way's orbiting stars settled into distinct populations. The thick disk contained older, redder stars, veterans of early turbulence, while the thin disk hosted newer generations enriched by heavy elements. In the halo above and below, ancient globular clusters traced elliptical orbits, fossils from the galaxy's youth. Even now, they circle silently, witnesses to 13 billion years of cosmic history. The entire system rotates once every 200 million years. Since its birth, the Milky Way has completed barely 60 revolutions. Time for a galaxy is measured not in days or centuries, but in orbits, each turn marking an epoch of evolution and transformation. Through all of this, gravity continued its tireless choreography. It required no conductor, no external command, only the mathematics of mass and motion. Every equation of celestial mechanics plays out here. Kepler's laws in the orbits of stars, Einstein's curvature in the bending of light, and chaos theory in the unpredictable paths of interstellar clouds. The Milky Way had become a living diagram of physics, where energy, entropy, and symmetry coexist. And as it turned, slowly, majestically, its spiral arms carried the dust that would one day form the sun, the earth, and us. In its graceful motion lay the promise of future worlds, each a brief spark in the galaxy's endless rotation. Galaxies are not isolated islands. They drift through the cosmic ocean in slow, gravitational dances, meeting, merging, and reshaping one another over billions of years. The Milky Way is no exception. Long after it formed its spiral structure, it continued to grow, not by quiet accretion of gas alone, but through encounters with its smaller neighbors. Gravity does not allow galaxies to pass each other unnoticed. Each approach distorts their shapes, drawing out long tendrils of stars known as tidal streams. These encounters leave ripples in the Milky Way's disk and waves of displaced stars in its halo. Though the sky above us seems serene, the galaxy is still ringing from collisions that began billions of years ago. One of the most dramatic of these events was the merger with the Gaia Enceladus galaxy. About 10 billion years ago, when the Milky Way was young, a smaller galaxy approached and collided with it at high speed. The impact tore Gaia Enceladus apart, scattering its stars into vast looping orbits that now surround the Milky Way like a ghostly halo. Many of the stars visible in our sky today, especially those rich in certain chemical fingerprints, were born in that vanished system. The merger stirred the Milky Way's disk, thickening it and setting off bursts of star formation. The scars of that encounter remain in the motions of old stars, detectable through precise mapping by the Gaia Space Observatory. Each stellar trajectory tells a story written in gravity, a memory preserved in motion. The Milky Way continued to feed on smaller galaxies long after that ancient impact. Around 5 billion years ago, it began tearing apart the Sagittarius dwarf galaxy, a fragile system orbiting close to our own. Each time Sagittarius passed through the Milky Way's disk, gravity stripped away more of its stars, stretching them into luminous streams that wrap around the galaxy like ribbons. These streams still glow faintly in infrared and visible light, encircling the sky in graceful arcs. Astronomers call them tidal debris, but the phrase hardly captures their beauty. They are the fossils of cosmic interaction, the handwriting of gravity across the night. Beyond Sagittarius, other dwarf galaxies also orbit our own: Fornax, Sculptor, Carina, Draco, and dozens of others. Some are little more than smudges of ancient stars, their gas long ago stolen by our galaxy's tidal field. Each will eventually merge with the Milky Way, adding its contents to our halo and fueling future generations of stars. This ongoing process, called hierarchical assembly, is how galaxies grow. Small systems combine to form larger ones, their stars and dark matter absorbed into ever greater structures. Even now, the Milky Way continues to evolve. The halo is not static, but alive, filled with streams and currents that drift through the dark like cosmic rivers. These encounters also create waves in the Milky Way's disk itself. When a dwarf galaxy passes nearby, it sends ripples through the plane of stars, like pebbles dropped into a pond of light. Astronomers have mapped these ripples using precise velocity data from the Gaia mission, revealing vertical oscillations in the stellar disk, hundreds of light years high. Such waves take hundreds of millions of years to fade, leaving the Milky Way perpetually quivering from ancient impacts. From our vantage point within the disk, we do not feel this motion, but it surrounds us. Every atom in our bodies moves through space on paths curved by gravitational memories of long-forgotten encounters. And still, the story is not over. Beyond our outermost stars lies a faint bridge of gas and dark matter, connecting the Milky Way to its nearest giant neighbor, the Andromeda Galaxy. The two are bound by gravity, slowly moving toward each other at hundreds of kilometers per second. In 4 billion years, they will collide, merging into a single vast elliptical system astronomers have already named Milkdromeda. When that day comes, new stars will ignite in waves of creation as gas clouds compress and collapse. The night sky of the far future will blaze with unfamiliar constellations, and the spiral shape of our galaxy will dissolve into something new. Cosmic encounters are not endings. They are transformations. The Milky Way, like all things in the universe, grows not by remaining still, but by embracing change. About 4.5 billion years ago, deep within one of the Milky Way's spiral arms, a quiet cloud of gas and dust began to stir. It had floated there for hundreds of millions of years, a remnant of countless generations of stars that had lived and died before it. Shock waves from a nearby supernova rippled through the region, disturbing the delicate balance of the cloud. Gravity, always patient, seized the opportunity. The cloud began to collapse inward, its atoms falling toward a shared center. As it shrank, it spun faster, conserving angular momentum, just as a figure skater pulls in their arms to spin more quickly. Within the dense core of that rotating nebula, pressure and heat rose until hydrogen began to fuse into helium. In that moment, the sun was born, a star like billions of others, yet destined to illuminate the only world we know. Around this newborn star, the leftover material formed a thin, swirling disk of gas, dust, and ice. Tiny particles collided and stuck together, forming pebbles, then boulders, then planetary embryos. Within a few million years, the disk was divided into regions. Close to the sun, heat drove away volatile gases, leaving rocky materials behind. Farther out, ices and lighter elements condensed, allowing giant planets to form. This structure would become the blueprint of the solar system. 4 rocky planets near the center, 4 giants beyond, and a vast halo of icy debris at the edge. The process was messy and violent. Collisions shattered some worlds, while others grew through relentless accretion. Planetary orbits shifted, scattering asteroids and comets across the young system in a chaotic ballet of creation. In the inner disk, a small planet formed from the collisions of countless fragments. Its surface was molten at first, reshaped by impacts from the leftover debris of formation. Over time, as the bombardment eased and its crust cooled, it developed a thin atmosphere and oceans of liquid water. This world, fragile yet resilient, would one day cradle life. Around it, the other rocky planets found their places. Mercury, scarred and baked by solar heat. Venus, cloaked in dense, toxic clouds. And Mars, smaller and colder, but once with rivers and lakes of its own. Each bore the marks of its birth, the physics of gravity and heat written into stone. Beyond the asteroid belt, the gas giants took shape. Jupiter, the largest of them all, grew quickly enough to capture vast amounts of hydrogen and helium, becoming a miniature star that never quite ignited. Its immense gravity shaped the rest of the solar system, deflecting comets, capturing moons, and even protecting the inner planets from excessive bombardment. Saturn followed, its icy rings forming later from shattered moons and leftover debris. Farther still, Uranus and Neptune condensed from the cold outskirts, pale blue sentinels guarding the edge of the solar frontier. Together, these planets brought stability to the system, their gravitational influences settling the orbits of smaller bodies into long-term harmony. Meanwhile, the Sun entered its long main sequence life, burning hydrogen in a steady glow. At its core, nuclear fusion balanced gravity perfectly, allowing it to shine for billions of years without change. From afar, the solar system appeared as a disk of shimmering dust, illuminated by a golden star, an ordinary sight in the galaxy, yet one filled with potential. The surrounding interstellar medium was enriched by the elements ejected from other nearby stars, a cosmic exchange of materials that continued unbroken since the dawn of the Milky Way. Within that exchange lay the molecules that would one day form DNA, ocean salt, and the air we breathe. Every chemical bond on Earth traces its ancestry to these ancient processes. And so, in a quiet corner of the galaxy, the Milky Way built a world capable of wondering about itself. The Sun, one of more than 200 billion stars, took its place among the spiral arms, orbiting the galactic center once every 200 million years. It has completed only about 20 revolutions since its birth, a brief heartbeat in cosmic time. The Earth travels with it, carrying life as a fragile bloom on a drifting grain of dust. From the vast perspective of the galaxy, the solar system is small, beyond comprehension, yet within it lies consciousness, curiosity, and memory, the universe reflecting on its own beginnings. The Milky Way's story had given rise to a storyteller. When the newborn Earth cooled, its surface was a landscape of fire and stone. Volcanoes exhaled oceans of steam into the thin air, and molten rock flowed across continents that did not yet exist. Over millions of years, the planet's crust solidified, and rain began to fall, first in storms of boiling vapor, then as cooler downpours that filled the lowlands with water. These were the first oceans, born from the same hydrogen and oxygen that had once drifted in the Milky Way's spiral arms. Lightning flashed across the turbulent skies, striking pools rich in carbon compounds. In those fleeting sparks of energy, simple molecules linked together into more complex forms, chains of carbon, hydrogen, nitrogen, and oxygen that would one day form the alphabet of life. The chemistry that unfolded on early Earth was guided by the same laws that govern stars. Heat drove reactions. Cooling allowed stability. In the planet's young seas, molecules collided, separated, and combined again, exploring every possible configuration. Among the countless failures, a few patterns endured. Some molecules began to replicate, using surrounding resources to make copies of themselves. Others formed protective shells, precursors of the first cells. Over time, these fragile systems grew more complex, evolving into networks of metabolism and reproduction, the hallmarks of living matter. None of it was planned. It was the natural consequence of chemistry in an environment rich with energy and possibility. Life was not an accident. It was a pattern written into the fabric of the universe. Beyond Earth, the seeds of life drifted through space. Comets and asteroids, remnants of the solar system's birth, carried water and organic compounds from the cold outer regions inward. Some of these bodies struck the young Earth, delivering carbon, nitrogen, and amino acids. Others seeded Mars, Europa, and Titan, scattering chemistry across the neighborhood of the Sun. Observations of distant interstellar clouds reveal that complex organic molecules, ethanol, formaldehyde, even simple sugars, form naturally in the cold vacuum of space. The universe itself seems predisposed to create life's ingredients wherever carbon and time coexist. Each comet tail, each icy grain of dust, is a messenger from the galaxy's chemistry lab. As the first microbial life took hold on Earth, the planet's atmosphere began to change. Early organisms fed on chemical energy, drawing it from minerals and heat vents on the ocean floor. Later, some learned to harness sunlight, using photosynthesis to convert carbon dioxide and water into oxygen. Over billions of years, this slow transformation filled the atmosphere with breathable air, turning a toxic world into a habitable one. The oxygen forged by life would one day allow fire, respiration, and thought. It would rust mountains and ignite engines. In the long dialogue between biology and geology, the planet itself became alive, reshaping its environment to sustain what it had created. Life and the galaxy remained intertwined. Supernovae seeded the planets with the heavy elements that made complex chemistry possible. Cosmic rays may have driven mutations that allowed evolution to adapt. Even the solar system's orbit through the Milky Way, rising and falling through the galactic plane every few tens of millions of years, may have influenced Earth's climate and the rhythms of extinction and renewal. On a timescale of hundreds of millions of years, the stars themselves act as gardeners, pruning and fertilizing the fields of life. Each pulse of radiation, each shift in gravity, writes another line in the long autobiography of the galaxy. And now, as we look up at the night sky, we see not strangers, but relatives. The calcium in our bones, the iron in our blood, the oxygen we breathe, all were forged in the hearts of ancient stars that died long before the Earth was born. Every cell in our bodies carries atoms that once blazed in supernovae scattered across the Milky Way. We are the galaxy made conscious, the universe learning to perceive itself. From hydrogen to thought, from starlight to memory, the story of life is the story of the cosmos awakening. The seeds that drifted through space have blossomed into awareness, and the Milky Way, through us, has found its voice. Today, the Milky Way is a mature galaxy, vast, intricate, and alive with motion. From edge to edge, it spans more than 100,000 light-years, a disk of 200 billion stars spinning around a central axis. Our sun orbits the core once every 200 million years, carrying its retinue of planets through waves of gas, dust, and starlight. If we could view it from afar, we would see a barred spiral, a shining whirlpool of light with arms unfurling from a golden center. Yet from within, we see only a narrow band across the night sky, a river of stars stretching from horizon to horizon. that faint glow, which humans named the Milky Way, is merely one glimpse of the grand structure that shelters our world. The galaxy's arms are still fertile. New stars are born in cold molecular clouds, where hydrogen gas collapses under gravity to form clusters of glowing suns. These nurseries, known as nebulae, are scattered throughout the disk. The Orion Nebula, the Eagle, and the Carina are among the closest examples. Vast caverns of dust and gas illuminated from within. Inside them, protostars flicker like candle flames, gathering mass and carving cavities in the surrounding haze. The energy of young stars sculpts pillars and arcs, revealing the invisible geometry of magnetic fields. Even after 13 billion years, the Milky Way continues to create, its spiral arms serving as both memory and womb. Between the stars lies the interstellar medium, a mixture of gas, dust, and plasma that fills the spaces we might mistake for emptiness. It is neither uniform nor still. Winds from supernova sweep through it. Cosmic rays dance within magnetic currents. Shock fronts ripple from ancient explosions long faded from sight. In this medium, temperature can vary from near absolute zero to millions of degrees. It is here that the great recycling of matter continues. Atoms forged in dead stars, drifting until gravity calls them together again. Every breath of interstellar gas is part of a process that will one day give rise to new systems, new suns, and new worlds. Beneath this visible beauty lies an unseen framework. The Milky Way is surrounded by a vast halo of dark matter, an invisible sphere extending far beyond the stars we can see. This dark component provides most of the galaxy's mass, binding the luminous disk and keeping it stable. Without it, the spiral arms would unravel in cosmic centuries. Astronomers map its presence through gravitational effects, the orbits of stars, the bending of light, the motion of satellite galaxies. What dark matter is made of remains one of the deepest mysteries of physics. It could be composed of exotic particles, undiscovered forms of matter, or perhaps something that challenges our very understanding of gravity itself. Whatever its nature, it shapes the Milky Way's fate as surely as the sun shapes the planets. At the center of the galaxy, Sagittarius, a star, still waits. A supermassive black hole, 4 million times heavier than our sun. Normally quiet, it occasionally flares when a cloud of gas ventures too close. Surrounding it is a bustling region of stars, some orbiting at speeds of thousands of kilometers per second. These orbits allow astronomers to measure the black hole's mass directly, confirming what Einstein's equations predicted a century ago. Yet even here, where gravity reaches its peak, there is balance. The surrounding stars, the magnetic fields, and the slow inflow of gas maintain a calm that belies the power hidden within. The Milky Way's core is not a place of chaos, but of equilibrium, the heart of a living system that has endured for billions of years. And still, the story unfolds. In the thin spiral arms, new civilizations may rise around distant suns. In the halo, old stars continue their endless journeys through the dark. Comets glide through the outer reaches, carrying fragments of ancient chemistry. The Milky Way is not static. It evolves slowly, subtly, through every cycle of birth and decay. When we look up at the night sky, we are not gazing into a museum of the past, but into a breathing organism that continues to change. Every photon of starlight that reaches Earth is a message from some corner of this vast system. a whisper across time, reminding us that we are part of a galaxy still in motion, still creating, still alive. The Milky Way drifts through space in silent motion, but even silence has direction. Around us, the universe continues to expand, and the great structures of galaxies move apart, like islands carried by a cosmic tide. Yet within our local group of galaxies, gravity still holds sway. The Milky Way and the Andromeda Galaxy are bound together, moving toward one another at a speed of nearly 400 kilometers per second. Though the distance between them is immense, more than 2 million light-years, their collision is inevitable. In about 4 billion years, the two spirals will meet, their stars passing harmlessly through one another, while their gas clouds crash, compress, and ignite new waves of star birth. The night sky of that distant age will blaze with thousands of unfamiliar suns. From the surface of the Earth, if any life still remains, the approaching Andromeda will first appear as a faint smudge that grows brighter with each passing million years. Over time, it will stretch across the heavens like a ghostly bridge of light. When the galaxies finally merge, their spiral arms will twist into vast tidal streams, and the central black holes will begin a slow, gravitational dance, orbiting each other for eons before joining as one. Their merger will release energy on a scale beyond imagination, sending ripples through the very fabric of space-time, gravitational waves strong enough to vibrate the cosmos itself. Astronomers of that future age, wherever they may exist, will witness a sight of sublime beauty. 2 galaxies becoming one. The new system, already named Milkdromeda, will likely take the shape of a giant elliptical galaxy. Its spiral structure will fade, replaced by a smooth halo of old stars, orbiting a massive central bulge. The bursts of new star formation triggered by the collision will briefly light the galaxy with blue brilliance, but the supply of gas will soon run low. Starbirth will slow, then cease, leaving behind an aging population of red and yellow suns. The Milky Way's long season of creation will end, and the galaxy will enter its twilight years. Yet even in this quieter era, beauty will remain. Clusters of ancient stars, vast arcs of dust, and the lingering hum of radiation that once powered so much light. Far beyond, the expansion of the universe will continue to accelerate. Dark energy, the mysterious force that drives cosmic inflation, will stretch the space between galaxies faster than gravity can pull them together. In tens of billions of years, even Milkdromeda will stand alone in a darkening void. The nearest galaxies will drift beyond the horizon of visibility, their light forever out of reach. To future observers, the universe will appear static and empty, the evidence of its beginning hidden beyond the limits of sight. The cosmic microwave background will fade, and the stars will burn out one by one. The universe will grow colder, quieter, and darker, though it will never truly end. It will simply change its rhythm once more. In that far future, the last stars will be red dwarfs, glowing dimly for trillions of years. Around some of them, planets may still orbit, warmed by the faintest of sunlight. When those stars finally fade, black dwarfs and neutron remnants will drift through the dark, each carrying the memory of the light they once gave. The supermassive black hole at the center of Milkdromeda will remain, slowly consuming stray matter and radiating faint Hawking radiation as it evaporates over unimaginable spans of time. Eventually, Even those black holes will vanish, leaving only cold particles and the faint quantum echo of their passing. The age of light will be over. And yet, in a way, the story never ends. The matter that once formed stars, planets, and life will remain, scattered thinly through an ever-expanding cosmos. Energy will still flow. Time will still move forward. Perhaps in another universe, or in a new cycle of creation. Gravity will once again gather dust into clouds, clouds into stars, and stars into worlds. The Milky Way's legacy will be written into whatever comes next. A trace of symmetry, a memory of beauty, a whisper of light. Every spark, every atom, every thought that ever existed in our galaxy will have been part of something eternal. The universe, in its endless silence, will remember stars are not born alone. They emerge in groups, forming families bound by gravity and origin. In the quiet depths of the Milky Way's spiral arms, massive clouds of gas and dust collapse under their own weight, fragmenting into dense knots. Each knot ignites as a newborn star, and together they form clusters, stellar siblings born from the same cosmic womb. In these nurseries, the air glows with the soft light of hydrogen emission, illuminated by the heat of young suns. It is in such clusters that the story of nearly every star begins, including our own sun long ago. Though they may drift apart over time, these families carry shared chemical signatures, traces of their common birth written in their starlight. In the first few million years of a cluster's life, the young stars burn brightly and fiercely. Massive ones live fast, fusing hydrogen into heavier elements at furious rates before dying in spectacular supernova explosions. The smaller stars, those like our sun, shine more gently, destined for billions of years of quiet life. Within the cluster, gravitational interactions create a constant dance. Stars approach and drift away, trading angular momentum like partners in a slow waltz. Over time, the cluster expands, and its members wander into the wider galaxy, scattering across thousands of light years. Some of these wayward stars will pass near one another again after billions of years, but most will never meet their siblings once more. Still, their chemistry and motion betray their shared ancestry to astronomers who can read the subtle fingerprints left behind. The Milky Way contains thousands of open clusters, each a shimmering pocket of youth. The Pleiades, the Hyades, and the Beehive cluster are among the best known, visible even to the naked eye on a dark night. Their stars are blue-white and hot, still burning the abundant hydrogen of their youth. Dust and gas linger around them, sculpted into delicate shapes by stellar winds and radiation. Open clusters are transient in cosmic terms. Most survive only a few 100 million years before dissolving into the galactic disk. Yet during their brief lives, they are laboratories of evolution, showing us how stars form, live, and part ways. Their existence reminds us that isolation is temporary, that even the loneliest star began in company. Further out, in the galactic halo, ancient globular clusters hang like lanterns in the night. These are not the nurseries of youth, but the elder statesmen of the galaxy. Dense spheres containing hundreds of thousands, sometimes millions, of old stars. Each globular cluster is a fossil from the Milky Way's early history, formed more than 10 billion years ago, when the galaxy itself was young. Their stars are dim, reddish, and metal-poor, containing few of the heavier elements created by later generations of supernovae. When we look at them, we are seeing the first children of the cosmos, still orbiting faithfully around their galactic parent, after eons of change. They are living museums of light, older than any mountain or ocean on Earth. Inside a globular cluster, gravity reigns supreme. Stars crowd so tightly that the night sky of any planet within would blaze with tens of thousands of suns. Some stars are pulled into close binaries, exchanging mass in intricate gravitational embraces. Others are hurled into interstellar space, flung away by dynamic encounters. Over time, heavier stars sink toward the cluster's center, while lighter ones drift outward, a slow segregation driven by mass and motion. This process, called relaxation, shapes the cluster's life for billions of years. At its heart, the densest clusters may even harbor intermediate mass black holes, ghostly anchors that keep the stars bound together against the endless pull of galactic tides. As clusters age, their brightest stars fade and die, leaving behind white dwarfs, neutron stars, and sometimes black holes. These remnants whisper of past brilliance, glowing faintly amid the dimming light of their neighbors. Over immense timescales, encounters with passing molecular clouds and the tidal forces of the Milky Way slowly erode the clusters. Stars are stripped away, one by one, until the remaining core dissolves into the galaxy's field population. Every cluster that vanishes leaves behind a trace, a faint stream of stars orbiting the galactic center, like the fading trail of a comet. The Milky Way's halo is full of these invisible fingerprints, the long echoes of families that once were. Even the sun was born in such a cluster. Astronomers have traced isotopic clues in meteorites and compared stellar abundances to identify possible solar siblings scattered across the galaxy. Somewhere, hundreds of light years away, there may still shine a star that formed from the same nebula as our sun, our cosmic brother or sister, orbiting silently through the night. Over 4.5 billion years, the cluster that gave us birth has long since dispersed, but its chemistry lives on, written in the elements of our world. Calcium in our bones, silicon in our rocks, iron in our blood. We are not only children of starlight, but members of an ancient, dispersed family. Clusters teach us how galaxies evolve. They reveal the rhythm of birth and death on scales larger than any world, and smaller than the cosmos itself. By studying the composition of their stars, astronomers can reconstruct the history of the Milky Way, how it gathered gas, how it merged with others, how it built its spiral arms. Each cluster is a data point in that cosmic biography, a chapter in a story billions of years long. When telescopes capture their light, we are not only seeing beauty, but deciphering memory, the memory of creation, preserved in motion and matter. In recent decades, space telescopes like Hubble and Gaia have transformed our view of these stellar congregations. We can now map their three-dimensional structure, track their motion through the galactic potential, and even detect subtle oscillations in their stars. Through these observations, clusters have become time machines, allowing us to look backward across cosmic ages. The Pleiades, only 100 million years old, show us the present tense of star formation. The globular clusters, ancient beyond imagining, reveal the prologue. Between them stretches the entire timeline of the Milky Way's stellar evolution, written not in words, but in light. Yet for all their grandeur, there is something intimate about clusters. They are reminders that the universe, though vast, is built on relationships. No star exists without influence. No light shines in perfect solitude. Gravity binds everything, galaxies, clusters, atoms, and even the fabric of time itself. Each star, no matter how far it travels, is forever linked to its origins by the invisible threads of history. When we look up at the night sky and see the faint shimmer of the Pleiades, we are witnessing that truth. The cosmos is a web of connection, and we are part of it. Someday, the Milky Way's clusters will fade, their members scattered across interstellar space. But their legacy will endure in every atom forged in their fires, every photon released from their fusion. The light of those lost families travels still, crossing time and distance to reach us. It mingles with the glow of countless others, blending into the luminous haze that we call the Milky Way. And as that light touches our eyes, for a brief and quiet moment, the galaxy remembers its families. It remembers where it came from, and so do we. Thus, among the spirals of stars and the clouds of gas, the story of the Milky Way continues to unfold. Each cluster that forms, each that dissolves, adds a verse to the song of the galaxy. It is a song of gravity and time, of birth and separation, of loss and continuity. To listen to it is to hear the heartbeat of creation itself, slow, patient, eternal. The clusters are its chords, the stars its melody. And through the ages, that melody never truly ends. It only changes key, echoing forever through the deep corridors of space. Between the stars lies not emptiness, but the substance of everything yet to come. The interstellar medium, an ocean of gas, dust, plasma, and invisible fields, fills the vast spaces between suns. It is the galaxy's bloodstream, circulating matter and energy through every spiral arm. Though it is tenuous beyond imagination, so thin that a single cubic centimeter may hold only a few atoms, it spans such enormous distances that its total mass rivals that of all the stars combined. This medium is where the Milky Way breathes, where old stars return their ashes, and new stars are conceived. It is the quiet interval between verses in the song of creation. The interstellar medium exists in many forms, each one a different temperature, density, and state of motion. There are cold molecular clouds, shadowy and vast, where hydrogen atoms pair into molecules and gather dust into veils. There are warm, neutral regions that glow softly in ultraviolet light. There are ionized plasmas, heated by the radiation of nearby stars, and hot cavities blown open by supernovae. Bubbles millions of degrees in temperature, expanding through the galaxy like invisible smoke rings. These regions coexist, overlapping and shifting like weather patterns in a planetary sky. Astronomers call this the multi-phase medium, a balance of chaos and structure, sustained by turbulence, radiation, and time. Each supernova reshapes this medium. When a massive star dies, it releases its outer layers at thousands of kilometers per second, slamming into the surrounding gas and sending shock waves rippling outward. Those waves compress nearby clouds, triggering new generations of stars even as they destroy others. The cycle of destruction and creation repeats endlessly. Every atom of carbon in your body once rode a shock front through interstellar space. The galaxy's expansion and contraction, its cooling and reheating, are not random. They are the slow respiration of a living system in which death and birth are inseparable. At the heart of this restless sea is magnetism. The Milky Way is threaded by magnetic fields, vast, invisible lines that twist and curve through the interstellar gas. Though incredibly weak by human standards, These fields shape the motion of plasma, guiding charged particles in spirals that trace the contours of the galactic arms. They influence how clouds collapse, how cosmic rays move, and how light is polarized as it travels through space. The galaxy's magnetism is ancient, perhaps as old as the Milky Way itself. It may have been seeded by the first stars and amplified by the slow rotation of the galactic disk. Today, it binds the interstellar medium together in a delicate web that pervades all things. If we could see these magnetic threads, the Milky Way would appear as a glowing tapestry of curves and filaments, like auroras stretching from one end of the galaxy to the other. In some regions, the fields align with the spiral arms, shepherding gas into lanes where new stars form. In others, they twist into loops and arches, sculpted by supernova explosions and stellar winds. The Planck and Sophia observatories have mapped their traces, revealing an intricate structure that connects scales from light years to thousands of parsecs. These magnetic filaments shimmer faintly in radio light, whispering the geometry of the unseen. They are the skeleton of the galaxy's invisible anatomy. Cosmic rays, high-energy particles born in supernova, travel along these magnetic highways. They move at nearly the speed of light, weaving through the interstellar medium and scattering off the field lines. Though they make up only a trace of the galaxy's mass, they carry enormous energy, enough to heat clouds, ionize atoms, and drive winds that flow out of the galactic disk. Some escape entirely, forming a faint halo of radiation around the Milky Way. Cosmic rays are both destroyers and creators. They break molecules apart, but also trigger new chemical reactions, forming complex organic compounds on the surfaces of dust grains. Through them, the galaxy writes chemistry into space itself. The dust that drifts through this medium is minute, but mighty. Tiny grains of silicate, graphite, and ice, often smaller than a wavelength of light, scatter and absorb starlight, reddening the glow of distant suns. These particles carry the chemical history of the galaxy: carbon from red giants, oxygen from supernovae, and iron from the cores of dying stars. Dust grains act as cosmic laboratories, providing surfaces where atoms can meet and form molecules like water and methanol. When clouds collapse to form new stars, that same dust helps cool the gas, allowing planets and life to emerge. The dim haze we see as the Milky Way's soft glow is, in part, the shimmer of this cosmic dust, our own origin shining faintly back at us. The interstellar medium is not static. It churns and eddies, driven by stellar winds, gravity, and magnetic turbulence. Gigantic bubbles of hot plasma expand from clusters of massive stars, merging into superbubbles that can span thousands of light years. These bubbles vent energy into the galactic halo, forming chimneys that channel matter out of the disk. As they cool, gas rains back down, feeding new waves of star formation. The Milky Way, in this sense, is a self-regulating organism, recycling its own material in cycles of collapse and renewal. It is a cosmic weather system, always in motion, yet always in balance. Astronomers study this invisible world through radio telescopes, which detect the faint emission of hydrogen at a wavelength of 21 centimeters. This single spectral line allows us to map the structure of the galaxy, tracing the arms and the motion of gas. Infrared observations reveal the glow of dust. X-rays expose the hot, violent regions where supernovae erupt. Together, these observations paint a picture of the Milky Way as a complex, layered system where every point in space is connected to every other through light, magnetism, and gravity. What seems empty between the stars is, in truth, alive with structure. When we imagine the galaxy, we often picture its stars, yet it is the space between them that gives the Milky Way its depth and dimension. Without the interstellar medium, there would be no stars, no planets, no chemistry of life. It is the dark soil from which all brightness grows. The photons we see from distant suns have traveled through this medium, scattered and shaped by its currents. Every star we look upon carries a trace of that invisible journey, a soft distortion, a hint of the magnetic dance that shaped its light. To gaze into the Milky Way is to look through an ocean that is both transparent and full. The magnetic web of the Milky Way connects every scale of existence, from the smallest particle to the grandest galactic structure. It is a bridge between matter and energy, chaos and order, light and dark. Even the solar system feels its pull as the sun's magnetic field interacts with the galactic one, bending and twisting the heliosphere into long, flowing tails. Through this connection, we remain in dialogue with the wider galaxy. The same forces that guide distant nebulae also touch the edge of our world, reminding us that we are part of something immeasurable and whole. In the quiet reaches between stars, far from the blaze of any sun, the interstellar medium hums with faint radio waves and the whisper of particles in motion. It is the Milky Way's heartbeat, steady and eternal. And though we cannot hear it, we are made of its rhythm. Every molecule in our bodies once drifted through that vast expanse, tracing paths along magnetic lines that curve through the night. To understand the interstellar medium is to understand the galaxy's breath, and to recognize that even the emptiest space is filled with the memory of creation. For most of human history, we looked to the night sky and saw the stars as points of mystery and distance, never imagining that each one might harbor worlds of its own. The idea that planets could exist around other suns was once speculation, a poetic thought whispered by dreamers. Yet now, within a single lifetime, it has become scientific fact. The Milky Way is not only a galaxy of stars, but of planets, billions upon billions of them, orbiting in patterns as diverse as imagination itself. Every twinkle we see may conceal a system like our own, with oceans, storms, and perhaps even life glimmering under alien skies. The first confirmed exoplanet discoveries came at the end of the 20th century. Astronomers detected the faint, gravitational tug of unseen companions pulling on their host stars, shifting their light by tiny amounts. Later, space telescopes like Kepler and TESS began watching thousands of stars, measuring minute dips in brightness as planets crossed in front of them. These transits revealed worlds of all kinds: hot Jupiters orbiting perilously close to their suns, super-Earths with dense atmospheres, and icy giants circling in the cold outer reaches. The data poured in faster than anyone expected. Within 2 decades, we went from knowing of none to cataloging thousands. The galaxy had been hiding a secret in plain sight. Planets are the rule, not the exception. Many of these worlds are strange beyond comprehension. Some are tidally locked, one side scorched in eternal daylight, while the other freezes in endless night. Others orbit 2 suns, where dawn and dusk come from different directions. There are planets of glass and iron, planets with rain made of diamonds, and planets so close to their stars that their surfaces boil into vapor. Yet amid the exotic lies, the familiar, astronomers have found rocky planets orbiting within the habitable zones of their stars, the narrow regions where temperatures could allow liquid water to exist. These are the worlds that ignite our imagination, the ones where life as we know it might take hold. The search for these potentially habitable planets has become one of the defining quests of modern science. We now analyze their atmospheres by studying the light that filters through them during transit. When a planet passes in front of its star, a fraction of the starlight passes through its air, imprinting spectral fingerprints of molecules, oxygen, methane, carbon dioxide, and water vapor. Detecting such combinations could one day reveal biological activity, the telltale signs of photosynthesis or respiration. The James Webb Space Telescope has already begun this work, measuring the delicate hues of alien skies hundreds of light years away. Through light alone, we may soon learn whether life exists elsewhere in our galaxy. Among the most intriguing discoveries are planets orbiting red dwarf stars, the most common stars in the Milky Way. These dim, long-lived suns can burn for trillions of years, providing stable light for unimaginable spans of time. Systems like TRAPPIST-1, with 7 Earth-sized worlds, have captured our collective curiosity. Yet red dwarfs also flare violently, releasing bursts of radiation that could strip planetary atmospheres. The balance between nurture and destruction is delicate. Life around such stars, if it exists, would be resilient, perhaps shielded beneath oceans or within protective atmospheres thicker than our own. The galaxy may already harbor countless such refugees of biology, quietly thriving beneath the faint red glow of distant suns. Exoplanets also tell us about our own origins. By studying their diversity, we see what paths the solar system might have taken had conditions been slightly different. Systems with migrating gas giants, tightly packed orbits, or tilted disks show that stability is rare. Our calm and spacious arrangement of planets may be unusual, a stroke of cosmic luck that gave Earth a long, steady era for life to evolve. The discovery of other worlds reminds us how fragile our circumstances are, and how easily the dice of creation could have fallen another way. The universe builds endlessly, but not all its creations endure. Beyond habitability, the sheer architecture of exoplanetary systems reveals the artistry of physics. Rings of dust circle new stars, forming planets through collisions and coalescence. Resonances lock worlds into orbital harmonies, where the tug of gravity keeps time like a cosmic metronome. Moons, asteroids, and comets form intricate patterns of motion, sculpted by invisible forces. Even chaos has rhythm here. The equations of dynamics play out like symphonies in motion. To understand these systems is to glimpse the hidden music of the galaxy, a music that began long before Earth was born and will continue long after it is gone. Some scientists now speak of galactic habitability, the idea that life may not be evenly distributed, but concentrated in regions of the Milky Way, where conditions are just right. Too close to the galactic center, radiation from supernovae and black holes may sterilize planets. Too far out, and there may be too few heavy elements to build complex chemistry. Between these extremes lies the galactic habitable zone, a vast annulus of possibility stretching through the spiral arms. Our sun happens to reside within it, orbiting quietly in a place of balance. Somewhere else in this zone, Other civilizations may gaze at their own skies, wondering if they too are alone. As we refine our instruments and techniques, we begin to imagine the next steps: direct imaging of Earth-like planets, mapping their continents and oceans, detecting the glimmer of city lights or the flare of volcanoes. Future missions may one day send robotic probes to nearby systems, propelled by light sails and guided by artificial intelligence. Even if such journeys take centuries, they will mark the beginning of a new age, when the children of the Milky Way start to explore their wider home. The dream of interstellar travel, once confined to fiction, now flickers within the reach of science. And still, amid all these discoveries, there remains a profound humility. We have found thousands of planets, yet we have not heard a single confirmed whisper of another voice. The galaxy may be teeming with life, or it may be silent. Both possibilities are equally staggering. If we are alone, then we are a singular bloom in a vast and indifferent void. If we are not, then somewhere, under a different sky, other minds may be looking back at us, sharing the same wonder. Either way, the stars invite us to keep listening, to keep searching, and to remember that discovery itself is an act of connection. Every exoplanet we find is a mirror, showing us what might have been, or what still could be. They remind us that our world is one note in a galactic chorus, a song of infinite variation. The Milky Way is not a cold expanse, but a garden of worlds, each shaped by the same laws of gravity and chance that shaped us. To look for other planets is not just to seek neighbors. It is to seek understanding, to know ourselves through the diversity of creation. The search will never truly end, for it is as old as curiosity itself. And so the story of the Milky Way continues, not just through stars, gas, and dust, but through the hidden multitude of worlds that orbit unseen. Some are barren, some perhaps alive. Some may already have risen, flourished, and fallen in the long history of the galaxy. Yet all of them, from the smallest rock to the grandest gas giant, share the same ancestry, born of starlight and time. When we gaze up at the sky, we are not looking at strangers. We are looking at a family of worlds, each one glowing softly in the dark, each one a possibility waiting to be known. Far beyond the glowing disk of the Milky Way, past the spiral arms and the luminous star clouds, lies a vast and lonely region, the galactic halo. To most eyes, it seems empty, but in truth it is filled with ancient light. Here, old stars wander through space, like travelers without a map. Their orbits are tilted, twisted, and elongated, tracing paths that remember collisions long past. The halo is the galaxy's memory, a realm where time moves differently, and where the ghosts of creation still drift in silence. The halo extends for hundreds of thousands of light years in every direction, enveloping the Milky Way in an invisible sphere. It contains the oldest stars we know, relics from a time before the galaxy had spiral arms or structure. Many of them are metal poor, forged in an era when the universe was young and heavy elements were scarce. Their light is faint and red, their lives slow and steady. These ancient suns carry within them the chemistry of the early cosmos, a record of what existed before the Milky Way became what it is today. Surrounding those stars is something even more mysterious: dark matter. Though we cannot see it, we feel its pull. The halo's mass is dominated by this unseen substance, outweighing all the visible stars by a factor of 5 or more. It forms a gravitational cocoon, binding the galaxy together and shaping the motion of its stars. Without it, the Milky Way's outer regions would fly apart. Astronomers infer its presence through rotation curves, how the stars orbit the center, and through gravitational lensing, where the halo's invisible weight bends light from galaxies far beyond. What dark matter is made of remains one of the great riddles of physics. But whatever it is, it holds our galaxy in its quiet embrace. Threaded through this dark architecture are streams of stars, the long tidal remnants of smaller galaxies devoured by the Milky Way. Each stream is the skeleton of an ancient collision, a ribbon of light tracing the path of destruction. The Sagittarius stream is among the most famous, a looping arc of stars that wraps around the sky. Others, like the Orphan stream or the Helmy debris, are fainter, but no less significant. Together, they tell a story of cosmic cannibalism, of growth through consumption. The halo is not static. It is still forming, still incorporating the ghosts of everything the Milky Way has ever touched. Some of these halo stars come from the first galaxies that merged to form ours. Others were born within the Milky Way's disk and later flung outward by gravitational encounters. When two massive clusters or black holes interact, they can hurl stars into intergalactic space, turning them into wanderers. These hypervelocity stars race through the halo at hundreds of kilometers per second, free from any gravitational home. Though rare, they are the messengers of violence, carrying the energy of ancient chaos into the calm of eternity. Globular clusters also populate the halo, like pearls on an invisible string. Each one orbits the Milky Way's center along an eccentric path, some plunging through the disk, others soaring high above it. They are the last survivors of the galaxy's formative years, their stars older than any civilization could imagine. Some may not even have formed within the Milky Way at all, but were captured from smaller galaxies long ago. In their dense cores, time seems compressed. Stars collide, merge, and occasionally give birth to black holes that dwell in near silence. To peer into a globular cluster is to look back across cosmic epochs, to witness the persistence of gravity and light. The halo is faint, but not dead. Gas flows through it in enormous streams, stripped from satellite galaxies or expelled from the Milky Way's own disk. These flows form a bridge between the visible and the unseen, linking the galactic ecosystem together. As the gas cools, it falls back toward the disk, feeding new cycles of star formation. The halo thus acts as a reservoir, storing the galaxy's future within its vast, diffuse volume. It is both graveyard and cradle, where the past dissolves into the next beginning. Observatories like Gaia and the Hubble Space Telescope have mapped this ethereal region in exquisite detail. Gaia's precise measurements of stellar motion allow us to reconstruct the halo's architecture in 3 dimensions. We can see ripples, shells, and waves, evidence of recent mergers still unfolding. The halo is a palimpsest of cosmic events, each collision writing a new layer over the old. To read it is to read history, written not in ink, but in motion, where every orbit is a sentence, and every cluster a punctuation mark. The outer halo fades gradually into the intergalactic medium, a frontier where the Milky Way's influence wanes. Out there, the density of matter drops to almost nothing. Yet even in that emptiness, our galaxy's gravity extends its reach. Beyond it lies the local group, a small collection of galaxies bound together in mutual orbit. The halo connects us to them, forming the bridge that will one day guide the Milky Way into its eventual union with Andromeda. In this sense, the halo is not an edge, but a threshold, the place where one identity blurs into another. Within the halo, cosmic rays and magnetic fields weave subtle patterns, interacting with the galactic wind that blows outward from the disk. This interplay of particles and fields generates faint radio emissions and diffuse X-rays. The halo is not as quiet as it seems. It murmurs in frequencies beyond our hearing. It is the low hum of the galaxy's metabolism, the sound of equilibrium between what is lost and what is gained. Scientists studying these signals are learning how energy flows between the Milky Way's visible and invisible realms, how light and gravity negotiate the boundaries of existence. To the human mind, the halo represents something more than a structure. It is the embodiment of memory. Every atom drifting there has lived 1,000 lives, forged in stars, scattered by supernovae, gathered again by gravity. These particles have witnessed the rise and fall of galaxies, the birth of worlds, the spark of consciousness. They are the ghosts of everything that ever was. When we gaze into the dark outskirts of our galaxy, we are looking at the long echo of time, the afterimage of creation that refuses to fade. And so the halo endures, vast and unending, a quiet border between the known and the unknown. It holds within it the stories of the Milky Way's past and the seeds of its future. It reminds us that even in apparent emptiness, there is continuity, that the universe forgets nothing. The light of distant stars may fade, but their influence lingers in the motion of the halo, in the invisible currents that shape the night. The ghosts that drift there are not lost. They are part of the endless rhythm of existence. In their stillness, the galaxy keeps dreaming. Light is the oldest language in the universe. Before words, before sound, before the first living thing opened its eyes, light was already speaking, crossing space, carrying messages from the beginning of time. Every photon is a traveler, born from the heat of a star or the collision of atoms, journeying through billions of years to arrive at a single instant of awareness. The Milky Way's history is written in light. From the earliest stars to the faint glow of the galactic halo, every flicker is a syllable in a cosmic poem that never ends. The stars of the Milky Way have been shining for more than 13 billion years. Their combined glow forms the faint ribbon that arches across the sky, so familiar and yet so profound. Each point of brightness is a sun, and around many of them circle planets, some barren, some vibrant, some perhaps harboring eyes that look back toward us. Light connects them all. It travels without rest, indifferent to distance, weaving a web of awareness through the galaxy. When we look upward on a clear night, we are not seeing the present, but the past. The memory of a light that began its journey before humanity existed, now meeting our gaze like an echo returned from eternity. Our own sun contributes its note to that galactic symphony. Every second, it pours out billions of tons of light and energy, most of which will never touch a planet. Yet a small fraction falls on Earth, where it fuels wind and weather, oceans and forests, thought and art. That energy, transformed and remembered, drives everything we are. Each heartbeat, each spark of consciousness is powered by starlight, we are not separate from the cosmos. We are its continuation, its way of perceiving itself. The light that shines on our faces each morning was born in the heart of a star. It carries the same essence that blazes across the Milky Way. Astronomers measure this light with careful precision. Telescopes on mountaintops and orbiting above the atmosphere collect photons from distant realms, translating them into images and spectra. But even the most advanced instruments cannot capture what light truly means, for light is both wave and particle, energy and information, presence and passage. It defines space and time, yet escapes both. The speed of light sets the rhythm of the cosmos, determining how we perceive causality itself. To study light is to study existence. To follow its path is to trace the shape of reality. Throughout the Milky Way, light tells countless stories. It reveals where stars are born, in glowing nebulae, where ultraviolet radiation makes gas shine like stained glass. It marks where stars die, in the expanding shells of supernova remnants, or the eerie flicker of pulsars. It illuminates the dust lanes that curve through the spiral arms, sculpting shadow and brilliance into the pattern we call home. Even in darkness, light finds a way to endure. When photons are absorbed by dust, they re-emerge in infrared form, warming the cold interstellar medium. Nothing luminous is truly lost. It simply changes its shape to survive. In the deepest reaches of the galaxy, near black holes and neutron stars, light bends and hesitates, its path curved by gravity's grip. Time itself slows in such places, and yet photons always find a way out, carrying with them the mark of distortion. This gravitational lensing allows astronomers to see the unseen, to map invisible masses and distant galaxies far beyond our own. Light is both messenger and mapmaker. It reveals not only what is, but what must be. Through its distortions, we glimpse the geometry of space-time, the hidden scaffolding that supports all things. When life first appeared on Earth, light shaped its evolution. Plants learned to harvest it, turning photons into food and oxygen. Eyes evolved to detect it, giving animals awareness of form and movement. For humans, light became a metaphor for knowledge, truth, and divinity. We learned to control it, to ignite it, to bend it into lasers and lenses. Yet even as we master light, we remain its subjects. We think in its reflections, dream in its colors, live by its cycles. The boundary between illumination and consciousness may be thinner than we imagine. Now, in the age of technology, we send light back into the cosmos. Our radio waves and laser signals travel outward at the same speed as starlight, carrying our greetings and our noise across the galactic sea. Somewhere, perhaps 1,000 years from now, those signals will reach another world, another mind. Whether or not they are ever heard, they become part of the Milky Way's story, a new kind of starlight, born not from fusion, but from thought. The galaxy that once gave rise to us now receives our answer, whispered in the same medium that first brought us warmth. There will come a time when the Milky Way stars begin to fade. Gas will run out, and the night will grow darker. The spiral arms will blur into a pale haze, and the galactic core will cool. Yet even then, light will persist. The remnants of stars will glow in infrared and radio waves. Black holes will release faint Hawking radiation. And long after the last luminous star flickers out, the memory of light will endure in the particles that once carried it. Frozen, perhaps, but eternal. The galaxy will sleep, but its legacy will remain, written into the fabric of space-time. For as long as there is light, there is meaning. Light carries not just energy, but continuity, the bridge between what was and what will be. Every photon that reaches us has survived an unimaginable journey through dust, gravity, and time. It reminds us that endurance is a kind of beauty, that persistence is its own creation. The Milky Way's legacy is not its size or age or shape, but its radiance, the simple, unstoppable act of shining. In that light, we find not only the galaxy's story, but our own. When you look up at the Milky Way, remember, what you see is both past and present, memory and dream. The light that touches your eyes tonight began its voyage when empires rose and fell, when mountains were still forming, when our ancestors were just beginning to wonder who they were. It has crossed the universe to meet you, to be seen, to complete its story. In that meeting, the cosmos becomes intimate. You and the galaxy are not separate things. You are one continuous thread of light, stretched across time. And so the story ends as it began, with light. The same light that formed the first atoms, that forged the stars, that gave life its spark. The same light that now travels through your mind as understanding. It is the Milky Way's gift, the eternal language of existence. Long after we are gone, it will continue to speak, whispering through the dark, telling the universe what it once was. We are part of that whisper, a brief shimmer in the great illumination. And though our time is fleeting, our light, too, will travel forever.